In this lecture, we shall be introducing abstract data types in Haskell. Consider the example of a stack data type. A stack is a collection of integers stacked one on top of the other. It supports two operations, push and pop. Push places an element on top of the stack, and pop removes the topmost element of the stack. You can see that this behavior is similar to lists. The push corresponds to adding a new element at the head of a list by using the colon operator. Pop corresponds to retrieving both the head and tail of the list. With this in mind, here is a definition of stack. We define stack as a type synonym for list of integers. Type stack equals list int. Now the push function can be defined as follows. Push, a function which takes two arguments, an integer and a stack, as inputs and outputs a stack. Push xs is nothing but x colon s. The head of the list is the top of the stack. Pop is a function that takes a stack as input and produces an int and a stack as output. The int is the top element of the stack, and the stack that is output is the stack after the top element has been removed. The definition of pop is as follows. Pop of x colon s prime equals the pair x comma s prime. So with this definition, the internal representation of stack is very evident. Stack is just a synonym for list of ints. The drawback is that this allows one to write functions that uses the internal representation. For instance, here is a function insert that inserts an element at the nth position from the top of the stack. Insert x n s. The x is an element to be inserted, n is the position, and s is the stack, and the output is also a stack. Insert x n s equals take n minus 1 of s plus plus the singleton list x plus plus drop n minus 1 of s. You see that here the internal representation of the stack, namely that it's just a list of integers, is used. One doesn't always want to allow such a use. For a stack data type, you would want to allow only the push and pop operations, and perhaps to check if the stack is empty. This motivates the definition of stack as an abstract data type, hiding the internal representation. We can define stack as a user-defined data type. Data stack equals stack list int. Recall that the stack on the left is the name of the type, the new type that we are defining, and the stack on the right is the so-called value constructor. The stack on the right is just a function from list of int to stack. The value constructor stack is a function that converts a list of int to a stack object. The internal representation is hidden. You can access a stack only through its constructor. Now we can define the following functions on this new data type. Empty, which returns an empty stack, and the definition is empty equals stack empty list. Push, which takes an int and a stack and returns a stack. Push of x and stack xs is stack of x colon xs. Here we use pattern matching on the user-defined data type, which is something familiar to us. Pop is a function that takes a stack and returns an int and a stack. Pop of stack x colon xs equals the pair x comma stack xs. IsEmpty is a function that checks if a stack is empty. It's a function from stack to bool. IsEmpty of stack empty list equals true. IsEmpty of stack anything else is false. The stack data type that we defined earlier was very specific in the sense that it stored only integer values. We might want to implement a stack that stores data of any type whatsoever. This is achieved by using polymorphic user-defined data types. which use type parameters. The definition is as follows: data stack A equals stack list of A. Recall that the stack on the left is a type name and the stack on the right is a constructor. When we use type parameters, the functions on the right are called value constructors, and the name of the type itself is called a type constructor, because for every instantiation of the type A, you get a new type stack A. For instance, if A is int, you will get a stack of integers. If A is float, you will get a stack of floats, etc. So the stack on the right is called a value constructor, and the stack on the left is called a type constructor. In a polymorphic type, the value constructor is nothing but a polymorphic function, which takes a list of A as input and produces an object of type stack A as output. In this particular case, we are also deriving EQ, show, ORD, etc. for this data type. We can define the following functions again: empty, which is a function that just returns a stack of type A; push, which is a function that takes an int and a stack A as input and produces a stack A as output; pop, which is a function that takes a stack A as input and produces the pair A comma stack A, one value of type A and a stack which is of type stack A as output. isEmpty is a function that takes a stack as input and produces a bool as output. The function definitions are exactly the same as given in the previous slide, except now that the types are more general. Sometimes functions on these polymorphic data types will not be completely polymorphic but only conditionally polymorphic. Here is an example. Suppose we want to sum all elements in a stack. We would achieve it as follows. Sum stack of stack x's is just sum, the function sum applied to x's. The function sum adds all the elements in the input list. What is the type of sum stack? Notice that the type of sum is a polymorphic function which is conditionally polymorphic. Its type is num A implies list A arrow A. Therefore, the sum stack function is applicable only if the stack has numeric elements. In other words, the sum stack function has type num A implies stack A arrow A. Earlier we said we can derive stack as a type which belongs to the class show, but this defines a default implementation for show. Show stack list 1, 2, 3 is just the string which says stack followed by a representation of the list 1, 2, 3 within square brackets. Suppose you want something fancier. Let's say we want to say show of stack 1, 2, 3 is 1 arrow 2 arrow 3 within quotes. The string 1 arrow 2 arrow 3. This means that we would have to define our own custom show function. So one can change the default behavior of show as follows. We say instance show A implies show stack A. This declaration means that stack A is an instance of the type class show, provided A is an instance of the type class show. Where the new definition of show, the small s show that we are defining, is show of stack L equals print elements L. The print elements function is given here. Print elements is a function from list A to string, provided A belongs to the type class show. Print elements of the empty list is just the empty string. Print elements of the singleton list containing x is just show of x. Print elements of x colon xs is show of x plus the arrow, the string consisting only of the arrow symbol plus print elements of xs. Notice the recursive call here. In this manner, we can define custom implementations of the functions that are provided by type classes. If we just say deriving capital show, we would get a default implementation of the show function, but we are always allowed to redefine the show function, in which case we are allowed to declare our data type to be an instance of the type class show. Let's consider another data type, Q. A queue is a collection of integers arranged in a sequence. NQ adds an element at the end of the queue. DQ removes the element at the start of the queue. Here is the definition. Data QA equals Q list A. Recall again that Q is the type constructor and the Q on the right is a value constructor, which is a function from list A to the type QA. The empty queue is just given by Q empty list. isEmpty is a function from QA to bool. isEmpty of Q empty list equals true. isEmpty of Q anything else is false. NQ adds an element to the end of the list. So NQX QXS equals Q of XS plus plus the singleton list X. DQ is a function that takes a Q as input and produces an element of type A and a QA object as output. DQ of Q X colon XS is the pair consisting of X and QXS. In this implementation, each NQ on a queue of length n takes order n time because we are adding the element at the end of the list. So NQing and DQing n elements might take order n squared time depending on the operations that we use. This is the worst case time that could be consumed by a sequence of n NQ and DQ operations. Here is a more efficient implementation of a queue. We use two lists and represent Q1, Q2 to Qn, the queue consisting of elements Q1, Q2 to Qn in this order as two lists. The first list consisting of some elements in this order, Q1, Q2 till Qi, and the second list consisting of the remaining elements in the reverse order, Qn, Qn minus 1, etc. till Qi plus 1. The second list is the second part of the queue after Q1 to Qi in reversed order. Now NQ can be made to add an element at the start of the second list and DQ removes an element from the start of the first list. Recall that adding an element at the start of a list is a much simpler operation than adding an element at the end of a list. Now there is a problem if we try to DQ from a queue where the first list is empty. If the queue itself is empty, then we cannot DQ from it. But if the queue is non-empty, but the first list is empty in our representation, then we need to reverse the second list into the first and remove the first element. This leads us to the following implementation. Data QA equals new Q. This is a new constructor. Typically the convention is that the value constructor has the same name as the type constructor or type name. But here, just to distinguish this from the earlier implementation, we call it new Q. New Q, and it's a constructor which takes two lists as arguments. So data QA equals new Q list A list A. Now the NQ function, as we described earlier, adds an element to the start of the second list. NQ of X and new Q Y's and Z's is nothing but new Q of Y's. The first list is retained as it is and X is added to the front of the second list, X colon Z's. DQ new Q of X colon X's Y's. This is the case where the first list is non-empty, is nothing but X comma new Q of X's and Y's. We have removed the first element from the first list and retained the second list as it is. dq of new q empty list wise, this is the case where the first list is empty. What we do is reverse the second list into the first position and take the second list to be the empty list and dq from here. So dq of new q empty list wise is nothing but dq of new q reverse wise empty list. This is seemingly a better implementation because every time we enqueue, we add to the beginning of the second list. But there are times when you have to reverse the second list into the first list, namely when the first list is empty. How much does this cost? If we add n elements to the queue, we get new queue of empty list qn minus 1 to qn. The next dq takes order n time to reverse the list qn to q1 into the first list. And if we dq once now, we get new queue of q2 to qn an empty list. But the beauty is that the next n minus 1 dq operations take only order one time. We paid order n time when we did this dq operation, but we were repaid by having to spend only constant time on the next n minus 1 dq operations, because all we had to do was just remove the element from the front of the first list. Therefore, on average, we will still be consuming order n time. This is made precise by something called amortized analysis. Here we precisely count how much time it takes to complete a sequence of operations rather than a single operation. Even though a single dq may take as much as order n time, when we consider a sequence of n instructions, the story is different. It is not that we take order n squared time for completing a sequence of n instructions. In fact, we only take order n steps to complete a sequence of n instructions. And the way to show it is as follows. Look at how many times an element is touched once it enters the queue. It is touched once when it is added to the second list as part of the enqueue, and it is touched twice when it is moved from the second queue to the first queue. This is when we do a dq operation when the first list is empty. And this element is touched once when it is removed from the first list. This is when we dq from the first list when this element was at the head. So therefore, each element is touched at most 4 times. Now, any sequence of n instructions involves at most n elements, and therefore, any sequence of n instructions takes only order n steps. To summarize, we have defined abstract data types in this lecture through the example of a stack and a queue. We have also defined polymorphic user-defined data types by showing how you can generalize the stack and queue data types to store not just integers but any data type A whatsoever by the use of supplying type parameters. The functions on these data types are polymorphic, but sometimes they are conditionally polymorphic, not freely polymorphic. For instance, for the function sum stack, etc., because the function makes sense only if the type parameter satisfies certain properties, like being a numeric data type, for instance. We have shown that we can use the instance keyword to define non-default implementations of functions like show. Finally, we looked at an example of how we can implement queues more efficiently and analyzed the efficiency of this new implementation by using the technique of amortized analysis.